Hi, my name is Ana Sofía Esquivel and I'm going to be presenting a risk comparison study between liquid and gaseous hydrogen and gasoline storage in refueling stations. My advisor was Juan Cristobal Torquia. Due to its absence of CO2 emissions, hydrogen is becoming increasingly relevant as a clean fuel in the transportation sector. However, despite the many technological advances made towards this fuel, its perception as an above-average risk factor has somewhat slowed down its development. While there are several safety concerns regarding the use of hydrogen, the perception of risk towards it should not be any different than from commonly used fuels such as gasoline. Aiming to provide a comparison parameter between hydrogen and gasoline safety, this study analyzes several physico-chemical parameters considered as relevant for determining a fuel's level of risk. A methodology is proposed for homogenizing these parameters into a numerical value for three different fuel types: liquid hydrogen, gaseous hydrogen, and gasoline. The fuels were assigned 22, 18, and 22 as levels of risk respectively, meaning that liquid hydrogen and gasoline are at the same level of risk, while gaseous hydrogen is significantly less dangerous. This approach proves to be valuable as the initial groundwork from which scenario-based studies can be specifically constructed when necessary. The relevance of this study arises in the context of hydrogen refueling stations' rapid growth throughout the globe, as well as the necessity for innovative safety technologies regarding the use of hydrogen. To provide a numerical answer for determining which of the three fuels has a higher level of risk, a simple methodology was used. Throughout the study, 8 physico-chemical parameters were discussed. For each of these parameters, an adimensional value was given, depending on the level of potential risk it represented. These values went from 1 to 3, 3 being the riskier fuel. In cases in which certain parameter didn't apply, a 0 value was given. Additionally, 3 different ignition-derived phenomena were also evaluated as possible or not possible for scenarios. For each, a value of 1 was assigned if possible and a 0 if not possible. Also, an already existing hazard classification methodology, the NFPA fire diamond, was included. The risk level assigned per category was added up for each fire diamond, resulting in an overall risk level per fuel. These assigned values were added up for each fuel. The fuel with a higher value, thus, represents a higher risk. Liquid hydrogen and gasoline resulted in an overall of 22 points each, whilst gaseous hydrogen presented only 4 points less. This difference in points puts liquid hydrogen and gasoline at the same level of risk, proving that, based on these criteria, the conceptualization of hydrogen as a riskier fuel is mistaken. On the other hand, gaseous hydrogen proves to be a safer fuel than gasoline. The presentation of a numerical answer is an advantage towards commonly used methodologies such as HACCP, which analyze risk in a qualitative way, focusing on human health and building damage-related consequences. Being able to analyze the fuel by itself instead of the affectations it can produce in case of a proposed accident scenario can be an opportunity for having a better understanding of the fuel itself, and consequently designing more appropriate safety technologies, codes, and standards. This methodology can be viewed as a first approach for a risk assessment. For the implementation of projects, an exhaustive scenario model must be made contemplating all the specifications and characteristics related, especially considering that the outcome of the utilization of risk assessment methodologies is in direct relation with safety issues and the preservation of human lives. This study lays a basis for designing risk determination models for specific scenarios when needed. The compilation of information and the general idea of the behavior of different ignition-related phenomena offer a groundwork regarding thermodynamic and physico-chemical risks presented in fuel storage. For future works, the specifically dangerous consequences derived from vapor cloud explosions, as well as the complexity of the physico-chemical and thermodynamic parameters that need to be studied in order to predict their performance, makes their study a topic of great interest. The use of methodologies such as acoustic modeling for studying VCEs seems to be an area of opportunity for developing safety technologies which could be based on utilizing an explosion's own properties as an advantage. Thank you very much.